Hey everybody, how's it going? Hope everybody's doing well. Happy hump day. Um, Sorry we had to switch things up a little bit this week. Normally I do these live streams on Monday nights, but had to do it on Wednesday night this week. As usual with these live streams, be sure to drop any questions you have in the live chat below. Today we're going to be going over a few interesting problems about finding the area between two different curves. And one of them is particularly interesting. Well, I think they're both actually particularly interesting for different reasons. But anyways, yeah. So one other thing I want to kind of point out before we go ahead and jump into this first problem, this first example here. A lot of the, well, both, the area between curves and then the other problem we're going to get into in a bit has to do with tangent lines also. These are topics that are on my Calculus 1 and my Calculus 2 study guide. Tangent lines are also covered in my complete Calculus 1 package. I put links to all those in the pinned comment below and in the live chat. If you're here live, they're in the live chat. If you're watching later, it'll be in the pinned comment. But this is going to be the first problem we're going to do here. So the problem tells us to find the values of C such that the area of the region bounded by the parabolas y equals x squared minus c squared and y equals c squared minus x squared is 576. So this is kind of an interesting problem because they give you these two different equations of the functions that we're trying to find the area between them. But they both have this c squared term in here, which is kind of different. You don't really see that too often. But what you want to kind of keep in mind with this is the c is going to be treated as a constant. So there isn't necessarily anything that tells us that c is a constant and x is a variable, except for just kind of the common expectation or the common notation that usually you have like y equals some function of x. So as a result of that, typically, if you have y's and x's and then some other letter, the x is going to be your input variable or your independent variable. The y is going to be your output variable or your dependent variable. And then the other letter is going to be a constant. And like I said, there definitely are situations where that is not the case. Usually if they don't specify or don't give you any context clues that would tell you that, you can pretty safely assume that x is going to be your input variable, y is going to be your output, and other letters, especially c is a very common one, would be constants. So what we should do first of all is just kind of draw a sketch of what we're dealing with here. So let's go ahead and start with that. Let's think about what each of these functions are going to look like. So first we'll start here, y equals x squared minus c squared. So like I said, x is our variable. So basically we have x squared minus some constant, right? So just imagine, what if we had like x squared minus 9, for example. 9 is just some number, just like c squared would be just some number. We don't know what c is. C is what we're trying to figure out, but excuse me. Whatever number c is, it's going to give us something that looks like this, right? Where we just have x squared minus some number. So as a result, what we can kind of do is think about what this will look like. Well, this is just going to be a parabola since we have an x squared term and then just a constant. The x squared term is positive, so we know it's going to be an upward facing parabola. So it's going to have generally this kind of a shape. And then it's going to be moved down, in this case, 9 units. In this case, it's going to be c squared units. But there is one thing really important here. C squared is always going to be positive, right? Just looking at c squared itself, this is always going to be positive because any number, whether you have a positive number or a negative number squared, it makes it positive. So c squared is going to be positive. So if we have x squared minus a positive number or x squared minus something like x squared minus 9, for example, we know we're going to have an upward facing parabola that is shifted down some number of units. So if we just had x squared, the function x squared, it would look something like this. And that was a pretty terrible sketch. It would look something like this. But since we have x squared minus some positive number, basically that's just going to shift this down some number of units. So basically, we would have something down here. And how many units is it going to shift it down is kind of the next logical question. Well, it's going to shift it down c squared units. So basically, we know that this vertex here is going to be at c squared, or negative c squared, actually. See a question here. What does a negative look like? So I'll get to that in just a second in this other function here, because that does have that. Good question, though. So basically, we know that this function is going to look something like this. We could actually even figure out where this intersects here, but I'll come back to that a little bit later, because that's going to be relevant in a later step. So now let's think about what this function looks like. So in this case, we have c squared, some constant squared, minus x squared. So that's, kind of similar to what we had over here, except in this case, now we have our constant being positive. Instead of over here, we had minus some constant. And then our x squared term is now negative. So what that's going to do, whenever you have this kind of a thing, we could also think of this as y equals negative x squared plus c squared. That's the same exact function. Since our x squared term here, since x is our variable, our x squared term has a negative coefficient. This one is going to be facing downward like that. It's going to be a downward facing parabola, where now the number that's being added, again, since c squared is always positive, any number squared is always positive. Now that we have a downward facing parabola plus a positive number, it's going to be shifted up c squared units. So very similar to what we had here. Now we're going to have a parabola which is shifted up c squared units and then comes down like this. And then again, since we shifted it up c squared units, this vertex here is at positive c squared. So this is kind of what our function or these two functions are going to be looking like. So the question obviously is, how do we find the area between these two functions if we don't know what c squared is or what c is? Well, let's start with the formula for the area between two curves. And like I said, this is one of the formulas that's on my integral calculus cheat sheet. There's a link down in the description or in the pinned live chat comment that I dropped over there, or in the pinned comment below. But that formula from my study guide basically tells us that if we want to find the area between two curves, so the area between two curves is going to be given by the integral of, and this isn't exactly the notation I use on my study guide. It goes into a little bit more detail in writing. But basically what we want to do is we want to integrate our top function minus our bottom function is essentially what it comes down to. So you can see throughout this area trapped between these two curves here, let's actually go ahead and even shade it in a little bit. We basically have this area in here. This is you can kind of see throughout this whole area. If we imagine for a second a red, we'll make it red so we can kind of distinguish between them, a vertical line that, let me grab this here. A vertical line moving throughout our area from left to right. So from over here at the left edge over to the right edge. If you imagine, and I didn't quite make this long enough, but you can kind of imagine this vertical line extending further so that it actually goes across the whole area. You can imagine this vertical line sliding across our area, and basically where this vertical line intersects with the edge of this shaded area is what we want to consider the top and the bottom. That's how we kind of figure it out. Sorry about that. Got a little tickle in my throat. So basically, as this vertical line goes across, you can see, let's take a snapshot right here, for example. You can see that the top of this this green shaded area is made up by this function right here, which is intersecting with our red line right here, our vertical line right here. And then same idea here. If we look at the bottom of this area, it intersects with this function down here. So what you notice as this vertical line goes across is the top edge of this area is always going to be this parabola here, all the way through from left to right edge. And then the bottom edge of this area is always going to be this parabola here. So it's consistent all the way through that this downward facing parabola is the top of our area, and this upward facing parabola is the bottom function of our area. So if we are going to find the area of this this area between these two curves, it's just going to be this top function, which is c squared minus x squared, minus this bottom function, which is x squared minus c squared. So minus, make sure you put this all in parentheses, minus x squared minus c squared. Okay, it is very important that this bottom function is in parentheses here, because if it is not, this negative sign is not going to properly distribute, and you're going to get the wrong number. So the other piece that we need to figure out now is the bounds of our integral. Well, the bounds of our integral are just going to be whatever x value is the left edge of our area and the right edge of our area. Well, like I said earlier, we would come back to figuring out where these parabolas intersect with the x-axis, or in other words, where they intersect with each other. In order to figure out where two functions intersect with each other, all you have to do is set them equal to each other. That's all it really comes down to. So what we can do is we can take x squared minus c squared, which is one of our functions, and set it equal to c squared minus x squared, which is the other one. And then keep in mind, what these bounds need to be is x values. We're integrating this with respect to x. So these need to be x values. So we need to solve this equation for x. It's fine if our answer has c's in it, because we don't know what c is. We can't possibly say that, say what number this is where these intersect with each other. But we can say what it is in terms of this unknown constant c. So we just need to take this equation and solve it for x. So let's move all of our x's onto one side, all the c's over to the other side. So we'll add c squared to both sides. We'll add x squared to both sides. So we get x squared plus x squared is 2x squared. C squared plus c squared is 2c squared. This cancels with this. This cancels with this. Then we can divide both sides by 2, getting x squared equals c squared. And then we can take the positive and negative square root of both sides, giving us x equals plus or minus the square root of c squared. The square root and the squared are going to cancel, giving us plus or minus c. So basically, this point right here is positive c, and this point right here is negative c. So that was important when you take the square root of both sides of an equation to solve for a variable like this. You do need to take the positive and negative square root in order to account for both of those. So basically what that tells us is that the left edge of this region is negative c, so that's going to be our lower bound, and the right edge of this region is positive c, so that's going to be our upper bound. So now you're probably looking at this integral and thinking, well, what the heck are we supposed to do with x's and c's? That doesn't make any sense. But keep in mind, there's still one more piece of information that our problem told us that we have not accounted for yet, and that is right here. We already know that the area of this region is 576. So if this equation is meant to represent the area of this region, we already know what this is equal to. We're not actually trying to solve for this here. We're trying to solve for c. We already know what this integral is equal to. It's going to be equal to 576. So kind of a weird situation there. Usually when you're trying to use this area between two curves equation, you're solving for the area. But in this case, we know the area. We're trying to solve for this other unknown constant. So what we can do now is we can simplify this integral. So to simplify this, we'll go ahead and distribute the negative sign. So that'll give us, this stuff isn't going to change out here, but negative x squared. So the negative distributes in there. And then the negative will distribute in here. Negative, negative are going to cancel. We're going to get plus c squared. Then we can combine our like terms. So we have negative x squared minus x squared is minus 2x squared. C squared plus c squared is plus 2c squared. Okay. So now we can go ahead and integrate this. So to integrate this, we can actually just do that with the power rule. So the power rule says that, whenever you have an x raised up to some power term like we have here, we can raise the power by 1, so making it x cubed, increase our power by 1, and then divide by our new power. So negative 2 is going to remain our coefficient, and then we'll divide by our new power, which is 3. So then this one, keep in mind, c is a constant. So if c is a constant, if c is some constant number that's not changing, that constant number squared is still a constant, and that constant times 2 is still a constant. So if you just multiply a bunch of constants together, or add or subtract a bunch of constants that are not variables, you still just end up with a constant. So this whole plus 2c squared term right here, this is just one big constant. So the reason why I bring that up is, well, how do you integrate a constant? Well, the integral of a constant is just that constant times x. So that is the integral there. And then we need to evaluate this from negative c to positive c. So in order to do that, we're just going to go into our equation and replace our x's with the upper bound, and then go back in and replace our x's with the lower bound. Whoops, this is 576 here. So we will get, first plugging in c, so we're going to get negative 2/3 times c cubed plus 2 times c squared times c. C squared times c is just c cubed, so plus 2c cubed. And then minus, parentheses, plugging in our lower bound. So now we're going to plug in negative c for x, so we're going to get negative 2/3 times negative c cubed plus, well, actually, let's do this. No, that's fine. We'll leave it like this. 2c squared times negative c. Okay, so now we want to simplify this, because this is a bit of a mess at this point. So to simplify this, first of all, negative c cubed is going to be just negative c cubed. Cubing the negative sign is going to keep it negative, and then cubing the c is going to make c cubed. So we're going to have basically this is negative c cubed. Similarly over here, this c squared times negative c is also going to give us negative c cubed. So basically, to simplify this, just what's in the parentheses here, we're going to have negative 2/3 times negative c cubed, which is the negatives are going to cancel, giving us positive 2/3 c cubed. And then plus, or I'm sorry, not plus. We have plus 2 times negative c cubed, which is going to be minus 2c cubed. And then remember, all this is just going to remain the same for now. Okay, so now we want to distribute our negative sign into the parentheses here. So we're going to get negative 2/3 c cubed, negative and negative cancel, giving us plus 2c cubed. All this will leave the same. All right. Keep doing that. Keep making it a 5, but it's a 6. 576. Yeah. Okay, so now we can combine our like terms. So now notice one thing that is very important. At this point, we have evaluated the integral from our lower bound to our upper bound. Typically, when you evaluate a definite integral with upper bounds and lower bounds like that, once you have evaluated the integral, once you have integrated this function and then plugged in the upper bound, plugged in the lower bound, and subtracted them, you should have a number. There should be no more variables left. What do you notice about this equation? There's no x's left. We only have these c cubed terms in here. Well, since c is a constant, again, c squared or c cubed or c to any power times any other number is still a constant. So we still just have a number over here. So we have evaluated the integral and we've gotten it down to a number. Of course, what the question asked us to find was find the values of c that make this work. So we need to find c. However, it is important to notice that we don't have variables here. We have basically integrated out our variables. We just have this constant that we're trying to solve for. So basically, we just have a bunch of c cubed terms being added together. Let's think about what they are. We have a 2 plus a 2, so that gives us 4. Minus 2/3 minus 2/3 gives us minus 4/3. So basically, 4 minus 4/3 is our coefficient. If we were to get a like denominator here, we would make this 12/3 minus 4/3. So that gives us 8/3. So basically 576 equals 8/3 c cubed. And then we could multiply both sides by 3/8. So we would get 3 times 576 over 8 equals c cubed. And then to solve for c, we would just have to take the cube root of both sides. So that gives us c equals the cube root of 3 times 576 all over 8. So I'll go ahead and leave this for you to finish up. All you really have to do at this point is just plug it into a calculator. If it were a test and you had to leave this in exact form, I'd probably just leave it where it is right there. But you could certainly just plug that into a calculator and get what that number c would be. All right. Not seeing any questions in the live chat. So we'll go ahead and carry on to the second problem that I have prepared for you. So this one is going to be a little bit interesting, a little bit unique and different. We are going to find the area of the region bounded by the parabola y equals x squared, the tangent line to this parabola at the point 1, 1, and the x-axis. So this is weird because what we have to do is we have to find a tangent line equation, and then we have to use that tangent line equation to find the area between two curves. So, or, you could think of it as like between a curve and a line. It doesn't really matter. A line still can be, thought of as a curve. So we're trying to find the area between these two curves, but we don't even know what one of the curves is. We actually have to find that. So this is pretty interesting because it's going to combine some topics from differential calculus and integral calculus and put them into one problem. So basically, we're going to be finding a tangent line equation and then the area based on that within the same problem. So first thing we need to do is figure out the tangent line equation. And like I said, tangent lines is one of the formulas on my Calculus 1 study guide or Calculus 1 cheat sheet. Link down in the description if you want to check that out. That we will need to start with that. So I have made several videos on how to find the equation of a tangent line at a point. So I'm not going to go into a ton of detail how to do this, but I will definitely kind of show you those steps. So first thing you want to do to find the equation of a tangent line of a function at a point, you want to think about what an equation of a line looks like, right? We're trying to find an equation of a tangent line. Should probably start with the equation of a line. Well, a line is always going to look like this. We're going to have y equals m times x minus x0 plus y0. So this is a tangent line with slope m, and it goes through the point x0, y0. So notice we have x minus x0, but it goes through the point with the positive x0 as the x coordinate. So basically, it's going to be minus of whatever x coordinate you want it to go through, and then out here, it's plus of whatever y coordinate you want it to go through. So we already know a point. We already know that this tangent line is going to be tangent at the point 1, 1. So we already know our x0 and our y0. They're both 1. So that's given. That's pretty straightforward. But we still need to find the slope. Well, how do you find the slope of a tangent line? To find the slope of a tangent line, whenever you see a problem that says find the slope of something, your brain should automatically go to derivative, right? Derivative just means slope. The derivative of a function tells you about that function's slope. So, there could be problems where they're going to say find the slope of something and you don't use the derivative, but generally, your brain should always think slope, derivative, slope, derivative, slope, derivative. Those two things go hand in hand like 99% of the time. So if we're going to find the slope of a tangent line, since a tangent line has to have the same slope as a function at the given point, we want to find the slope of our function at that point. Well, to find the slope of our function, y equals x squared, like I said, we need to find its derivative. So the derivative of x squared is just going to be the power rule. We'll bring the power down in front, bring the 2 down in front, keep our x as x, and minus 1 from our power. 2 minus 1 is 1. So x to the 1 is just x. So our derivative is 2x. But now keep in mind, what we need this tangent line to have the slope based on a specific point. We need it to be based on this point right here, 1, 1. So we only want to use our derivative to find the slope of our function at the point where x equals 1. So when x equals 1, that's the slope we want. So we want to plug in x equals 1 into our derivative to get the slope of our original function at x equals 1. So doing that, we're going to get 2 times 1, which is just 2. So we know that this function, y equals x squared, has a slope of 2 at the point 1, 1. So what we can do is take this slope of 2, and that's going to be our m, right? So now our tangent line equation is just going to be 2 times x minus 1, because 1 is our x0, plus 1, which is also our y0. Of course, from here, we can definitely simplify this to make the rest of our problem a little bit easier. Distribute the 2, giving us 2x minus 2 plus 1. Simplifying the negative 2 and the plus 1 gives us 2x minus 1. So this is going to be the equation of the tangent line to this function at the point 1, 1. So basically what we're trying to do now we've completed the first half of the problem. What we need to do at this point now is kind of imagine a separate problem where they just say, find the area between the curves, y equals x squared, y equals 2x minus 1, and the x-axis. Well, the x-axis is the same as saying y equals 0, right? The x-axis basically has the equation of y equals 0. So essentially what we're trying to do here is find the area of the region bounded by these 3 functions right here. So in order to do that, like I said, in the prior examples we went through, first thing you want to do with any of these find the area between the curves problems is to graph it. That's always going to help make things a lot easier for you. So let's start with the graph. So first of all, y equals x squared. That's just going to be a parabola with the vertex at the origin. That's relatively straightforward. The line y equals 2x minus 1. Well, kind of a little shortcut of what that's going to look like. We know that it's going to be tangent to our function at the point 1, 1. So right here at 1, 1, we know that this line is going to be tangent to our function. So basically we know right off the bat it's going to look something like this. That's not the straightest line, but I think you get the idea. We could, similarly just figure out, -1 is the y-intercept of this line based on the fact that we have 2x minus 1 here. And the slope is positive 2. So Basically, that's going to give us a line like that. And then we also want to look at the x-axis, or the line y equals 0. So you can see this little region right here that we're trying to find the area of. What's basically, trapped in between those three functions there. So this is an interesting one because we have a couple different options here. Generally when you're doing these, find the area between two curves, you want to think about whether you want to integrate horizontally or vertically, whether you want to think about like a horizontal line slicing through this region or a vertical line. Well, let's think about each of those real quick. First, we'll start with the horizontal line. So notice as this horizontal line cuts through our area, cuts through this orange shaded region here, think about where the right edge of this orange area and the left edge of this orange area intersect with this horizontal red line. Well, you notice basically from the point where they intersect right here, all the way down to the bottom edge of this area, you can see all the way through that whole region, the right edge of this orange area is this line function that we have here. And the left edge, basically the point where this red line intersects with this orange region here, on the left edge is always this parabola. So basically we have the same left edge and right edge function. The right edge function is this linear function the whole way, and the left edge function is this parabola the whole way. And it's just going to go from the bottom of this area here up to the top. Okay, so let's think about now what it looks like if we have a vertical line going through the whole way. So if we have a vertical line going through the whole way, things don't quite work out the same way, because let's think about as we go from the left to the right. So right here at this kind of little corner spot right here, as we first start getting into this, the bottom edge of this orange region is the x-axis. And the top edge of this orange region that intersects with this line is the parabola. Okay. But then as soon as we get to right here, basically the right half of this, you can see that the bottom edge of our orange region is the linear function, the line, and the top edge is the parabola. So basically for everything right of where this line is here, we have the top being the parabola, the bottom being that line. Everything to the left of it, we have the top being the parabola and the bottom being a different line. So basically we have two different top and bottom functions, which is not great. You don't really want that. So when we went horizontal, we had the same left and right function all the way through. That's definitely better. So we want to integrate this horizontally, which means we're going to integrate with respect to y, which means what we need to do is take our equations and solve them for x. So let's go ahead and do that. Let me just erase a few things here. Sorry, I'm getting a little bit of lag here. Come on now. All right, there we go. So what we want to do is get these equations to be x equals something instead of y equals something, because that will allow us to integrate in the other direction, essentially, than how this is going to do. Because if you have y equals, you have to do the vertical split. If you have x equals, that's how you set it up for the horizontal line splitting it, which is what we want. So let's take these two equations and just solve them for x. So first of all, y equals x squared. We just have to take the square root of both sides. So that's going to give us x equals plus or minus square root of y. Basically, the positive square root is going to be the positive portion of the positive x value portion of our parabola. And then the negative square root is going to be this negative x value parabola portion. So what we want is the positive portion, because we can see that this whole region is all on the positive portion. So we don't actually need the negative square root here. So we're just going to take x equals the positive square root of y. And we're going to use that half of our parabola. Okay. Then this function here, y equals 2x minus 1, we're going to, again, solve for x. So we're going to add 1 to the other side. Y plus 1 equals 2x. Divide both sides by 2. X equals 1/2 y plus 1/2. Okay. So now you want to think of this linear function as 1/2 y plus 1/2. Think of this parabola as the square root of y instead of what we had up here. So now we're going to use the equation, which, like I said, is on it's an equation on the integral calculus cheat sheet that I have, the Calculus 2 study guide. There's a link down in the pinned comment below and in the description if you want to check that out. But like I said before, the formula on there is basically to find the area between two curves, or area bounded by, a region bounded by some curves. You're basically going to integrate the top function minus the bottom function. Well, this is a little bit weird because what we have here is the right function and the left function, because we're imagining a horizontal line going through where we have, this line on the right edge and this parabola on the left edge. So we're actually going to think of this as the integral of the right function minus the left. And the equation on my study guide does definitely, explain this a little bit more, but I'm explaining it through the video. So I'm just going to write left and right because I think that's a little bit easier to understand. And I really want to show you how to use this formula too, so you can apply it yourself. So we're going to have the integral of the right function minus the left function. Well, like I said, this right function all the way through the whole region is this line, which we know has this equation right here, 1/2 y plus 1/2. So we're going to have the integral of 1/2 y plus 1/2 minus the left function, which is the positive square root of y. So we're going to have minus the square root of y. Now, generally, when you do this right minus left, top minus bottom, you want to make sure to put parentheses around the left or the bottom function. In this case, it only has one single term. So minus, putting parentheses there isn't going to make a difference in this case because the negative sign doesn't have to distribute to multiple terms. So now this is the thing we're going to integrate. And since we got it all in terms of y, since we're integrating with a horizontal line moving vertically through our area, we're going to integrate with respect to y. Basically, you want to think of that as you integrate with respect to whatever variable your line is going to go throughout. So since we have a horizontal line that we're moving vertically, it's going to go through a range of y values as it moves up and down. So we're integrating with respect to y because it's taking on a range of y values. Basically, this line would be like y equals some number. If you have a vertical line, that would be x equals some number. So you'd integrate with respect to x. In this case, we have y, so we're going to go dy. Now we need to think about what are the range of y values that this horizontal line is going to have, or that it's going to take on. Well, it's going to start down here at this bottom edge, which we know is y equals 0, and it's going to go up to this point where they intersect. Well, fortunately, we already know that because we made our tangent line specifically to go through that point and to intersect with our parabola at that point. So we already know that that point is 1, 1. So basically the y value there is 1. So essentially, the range of y values that we're going through is from y equals 0, the bottom edge, to y equals 1, where these intersect the top edge of our region there. So this is going to be the function that we're going to integrate to find the area between these curves. So first thing I'm going to do before actually integrating that is to reformat this just a little bit. Instead of taking the square root of y, what you want to do is think of that as y to the 1/2 power, because that's going to make it a lot easier to integrate this because we're going to be able to use power rule. So now to integrate this, we can just use power rule for basically all these, or I guess the first and the third term here. Power rule says that we're going to raise our power by 1 since we have some number times our variable y. Keep in mind, since we have a dy here, y is now our variable. So we're going to take y, raise the power by 1. When you don't have a power, it basically means that the power is 1. So we're going to raise it up to 2. And then we divide by our new power. We already had 1/2 out here. Dividing 1/2 divided by 2 is going to be 1/4. The integral of a constant basically just adds your variable to it. So it should not add, sorry, multiply it by your variable. So the integral of 1/2 is just 1/2 y. And then again, here, we're going to raise our power by 1. So 1/2 plus 1 is the same as 1/2 plus 2/2, which is 3/2. So the power of this is going to be 3/2. And then we divide by our new power. Dividing by something is the same as multiplying by the reciprocal of that thing. So instead of dividing by 3/2, we're going to multiply by 2/3. Okay. Now we're going to evaluate this from 0 to 1, which basically just means plug in 1 for all of our y's first. So that'll be 1/4, 1 squared, 1/2 times 1, 2/3 times 1 to the 3/2. And then we're going to minus, in parentheses, whatever we get from plugging in 0 for all of our y's. So 1/4, 0 squared plus 1/2 times 0 minus 2/3 times 0 to the 3/2. Okay. Make sure you put all of this in parentheses here, whatever you get from plugging in 0, because you need this minus sign to distribute to all those terms. I know I say that a lot, but it's a common mistake, and I just want to make sure you have that reminder so you don't miss that. So let's go ahead and simplify this. 1 raised up to any of these powers is just going to be 1. So 1/4 times 1, 1/2 times 1, negative 2/3 times 1. That just gives us 1/4 plus 1/2 minus 2/3. Then 0 raised up to any of these powers is just 0. 0 times any number is 0. So all of these in here are just 0. So we're just going to have minus 0, which just does nothing. So now we want to add up these fractions. We're going to need a common denominator. So 12 is probably our best bet. 4 times 3, or I'm sorry, 3 times 4 gives us 12, which is divisible by 2. So 12 is the best common denominator here. So 1/4 is the same as 3/12. 1/2 is the same as 6/12. And minus 2/3 is the same as minus 8/12. So we have 3 plus 6 is 9, minus 8 is 1. So 1/12. And that's going to be the area between these curves based on the tangent line that we had to find at the very beginning. So just 1/12 is going to be your final answer. I'm not seeing any questions in the live chat about that, so we'll go ahead and wrap things up there. Hope you found this video helpful. If you did, please be sure to hit that like button down below. Hit that subscribe button as well while you're down there, so you can be notified of each time I'm going live. I do these live streams typically every Monday night at 5 o'clock Pacific time. So I hope to see you there next week, and we'll keep on learning calculus together. Thanks, and see you then.